So now that we've seen one example of a trig substitution, we want to kind of take a look at sort of the more general way that we're going to do this. So how we're going to set each of these up, it's going to kind of depend on what type of square root we have in our problem. So here's the three types of triangles that we're going to use based on if we have that perfect square number minus x squared. Whoops, that was from our last video, wasn't it? And or if we have those perfect squares being added, then it's the hypotenuse. If we have our x perfect square minus our number perfect squared, then it's going to be our opposite side. So with each of these, in this first triangle, we'll call this triangle number 1 here, and then we've got triangle number 2 and triangle number 3. So in triangle number 1, this is what we used in the last example, and where we get that x equaling a times sine of theta, again, that just comes from our trig ratios, that it's the opposite side over the adjacent side, and then we multiply both sides by a, and we get x is equal to a times sine of theta. And then also from this, we can see, again, using our trig identities, that cosine of theta is equal to the square root of a squared minus x squared over a, or we might need to use that as a times cosine of theta is equal to the square root of x squared minus a squared. And when we're doing these also, we're going to do a substitution. We're going to change our variable from x to theta in our integral. So we're going to take this relationship, one where we have x is equal to something, just plain old x, and we're going to take the derivative of this. And when we do this, x equals sine of, or a times sine of theta, we're taking the derivative of each side, and we're getting a cosine of theta as our derivative, so that dx is equal to a cosine of theta d theta. So I'm going to underline these sort of three relationships here, that these are kind of the three big relationships that we're going to use if we've got the square root of a squared minus x squared in our integral. These are the three relationships that we're going to use to take our variable from being x to being theta instead. And again, as I mentioned in the last one, we totally, absolutely could swap what we label those two sides. What that's going to do is change all of the sines to cosines and all of the cosines to sines in everything that we have listed down below. It's also going to create a negative in that dx equaling a times sine of theta d theta. And so we use this setup the way that we do so that we avoid that situation. And that's what we're doing with each of these. Because again, we could absolutely swap where we put a and x all the time in these, or what's our opposite side and our adjacent side. That's kind of a better way of saying it. We could always flip-flop those. But what we've done is trying to keep this in terms of sine and tangent and secant, those trig functions that we generally use, those ones that don't come up with negative derivatives. So that's kind of been that's the point of why we set them up the way that we do. For the second triangle, we're going to have that x is equal to a times tangent of theta. And again, that's from, again, just our trig ratios. That is the opposite side over the adjacent side. So we get a times tangent of theta is equal to x. And then our square root, that's actually equal to secant of theta, which is our hypotenuse, over our adjacent side. So you can get to this relationship this way, or you actually could get to this relationship by taking that square root of a squared plus x squared, and replacing x squared with our a tangent of theta. And you could factor out that a squared plus 1 plus tangent squared of theta, and then replace 1 plus tangent squared of theta with secant squared of theta. And you absolutely get a plus secant of, or a times secant of theta. So you can kind of view it whatever way you want. This little bit here is kind of an aside. Whoops. Kind of another way that you could get to that relationship. But you can always think about it from the trig ratios too. And again, the reason why we want to do this is that we want to take this relationship right here and this relationship right here and use those to substitute in our integral. But we're also going to need to change our variable from x to theta. So we're going to take this relationship that x is equal to a tangent of theta and differentiate both sides. The derivative of tangent is secant squared of theta d theta. So these three guys that I've highlighted in red there, those are going to be the three relationships that we use to change our integral from being in terms of x to being in terms of theta. And so similarly with our third triangle, let's grab a different color here. This is if we have that x squared minus our perfect square number. And here, again, we're using that secant of theta is equal to our hypotenuse over our adjacent side, and we get that a secant of theta is equal to x. And then similarly, either with a trig ratio or with this sort of process that we have highlighted in blue there, we can get that a tangent of theta is equal to the square root of x squared minus a squared. And then if we take the derivative of what we have, let's see, what color do we want to highlight in? Maybe we'll highlight this in, trying to come up with a color we haven't used. There we go, green. If we take and differentiate our a secant of theta is equal to x, we're going to get a secant of theta times tangent of theta d theta is equal to dx. So these are the three relationships that we're going to use if we have this type of square root to change everything from our x variables to our thetas. So we did an example of triangle 1 in the first video. So let's take a look at an example that uses the second triangle here. Because, and again, we know it's the second triangle because it's that x squared plus our a squared. And if you want, you can rewrite this as 1 over the square root of x squared plus 4 squared dx. And that can kind of just help us remind us what each piece is here. So when we have our two numbers added, that square root, that's going to be our hypotenuse. So we're going to have, here's our angle, theta. So our hypotenuse is going to be x squared plus 4 squared. And our opposite side is going to be x, and our adjacent side is going to be a. And actually, we know a, in this case, it is 4. So our relationships that we're going to have here is we're going to have x is equal to 4 times tangent of theta. The square root of x squared plus 4 squared is equal to 4 times secant of theta. And dx is going to be 4 times secant squared of theta d theta. So again, you can get all of those from just the trig ratios of this triangle, or we can go back up here to this middle triangle and what we have circled there in red, replacing a with 4, because that's our a in this case. So here's our three relationships. And let's see, what do we have here? So we have 1 over, at the bottom of this fraction, we've got our square root of x squared plus 4 squared. So that's our 4 secant of theta. So maybe let's underline. That was already underlined in green, so we'll underline that in green, and we used that. And then the last thing that we need to replace is this dx. And dx is 4 times secant squared of, or times d theta. So 4 times secant squared of theta, d theta. And our integral is totally now in terms of theta. We can take this integral. This is much easier than the one that we had in the first video because a bunch of stuff cancels. That 4 in the bottom cancels with that 4 in the top. And maybe what we'll do is rewrite this one time so that we can have, a clear view of how we did the substitution and then a clear view of how we simplified this. So you can go back later and make sure that you know exactly what happened here. So those 4's cancel because we have 1 on the bottom of a fraction, 1 on the top. Same with our secants. We have 1 on the bottom and 2 on the top. So that leaves us with just a secant of theta. So our integral, like I said, is much easier than the one we had last time. We get the integral of secant of theta d theta. This is one that we know. We've used this one before. This is the natural log of secant of theta plus tangent of theta plus c. And now we have to substitute back. We've got to get everything back in terms of x. And if we look back up here, where we set up our triangle, we know what tangent of theta is, we know what secant of theta is. We have to take those relationships and rewrite them a little bit. Right? We have to actually write them as the trig ratios. We have to kind of go backwards. So the x equals 4 is tangent of theta, and the square root of x squared plus 4x squared over 4 is secant of theta. So let's go and do that in our integral. So we've got the natural log of the square root of x squared plus 16 over 4 plus x over 4. And so again, we have it here. We're done. This is our integral. There's a little bit that we can do to simplify this. Inside of that natural log, we've got a common denominator, so we could go ahead and add those. Adding the numerators is kind of boring because we can't actually add them. But we can write them next to each other over 4. We could use our property of logarithms to split this up as two separate logarithms if we wish. We don't necessarily have to. And what we could do if we wanted to at this point is all of this part here that I have circled in red, all of this is a constant. So what we could do if we wanted to is envelop that natural log of 4 in with our plus c. We'd have to label it a new constant, but we could do that. We could label it plus b, because it's a new number. It's that natural log of 4 plus whatever constant we had before. So we could do that. But again, I'm pretty happy if we can get to right there.